Welcome back. Today is March 30th, Monday. Notice our goal today is just to do one thing, and that is to come up with a particular angle of rotation theta that is necessary to eliminate that problematic XY term. You do have a problem set. It is just a couple examples to give you direct feedback. Please make sure you check the solutions manuals before you submit it formally to myself to identify any mistakes, and if you cannot, communicate to me and we'll figure it out together. Let's review the last class previously. We, after recognizing this equation defines conics for us, were given a hypothetical problem and a particular angle of rotation. We recognize, I hope that was the key lesson, we would never do this in this particular situation because it seems college algebra approach is much quicker and easier to understand. But nonetheless, you have developed two rotation formulas: substitution, evaluation of trigonometric unit circle values, root 2 over 2. Those particular x and y values are thrown into this equation. You recognize that in the process of completing the square, you eliminated the xy term, and you were led to this, a horizontally opening hyperbola. But of course, it was not horizontal because we rotated the axis 45 degrees. Let's do this now in theory. By theory, I mean we're going to develop a way that will allow us to always successfully rotate the axes no matter what A, B, C, D, E, or F is, and more importantly, given any particular angle of theta. I'm going to take my rotation angles, and I'm going to do exactly what I did the previous day. I'm going to plug in the given value of theta, which means now we're going to do this theoretically. Excellent job. The next step was to take our equation. This represents any equation I can throw your way, and plug in the appropriate rotation values anywhere you see an X or a Y. Your first thought, and that's my first thought when I first learned this way back in the day, was, whoa, what exactly will this look like? If I was to do this in class, we would probably be writing across all four boards in the classroom. But since I'm not, I've split it up to a couple different slides for you guys. So let's take a look at this first term, ax squared first. Anywhere I see the x, I'm going to replace it with this right here. It looks like only the x term is being squared, so I'm going to leave this a out in front. And that's what I'm looking at. Distributive property applies. I'm squaring a binomial. Just be very careful because you do have multiple factors within each term. Avoiding all algebraic mistakes leads me to that beautiful expression right there. Something only that a college trig student would be able to understand. Reminders, cosine and sine of theta values are simply ratios. They're just all numbers. All of this is just representing numbers. BXY term, I'm going to use this and that. I'm going to throw them in. I'm going to not distribute the B value at all. I'm just going to let the math, which is this right here, run its course, and maybe a little later on I'll sort my way through this jumbled mess and see what I end up with. Hopefully avoiding all algebraic mistakes. Please make sure to take the time to do this on your own. See if you end up with the same thing, and or you certainly may follow along with your textbook where the proof is given to you. X squared, BXY. We are good. We are good. Let's move on to the other terms. CY squared. Now I just need the rotation formula for Y, which you should have memorized by now. There it is. I'm going to avoid the C right now. I'm just going to square this binomial. Doing all this math correctly leads me to here. This is getting quite horizontally long. The dx term and the EY terms are very easy because there's no math to be done. I'm just going to plug in x for x. Not doing anything with the d yet, and y for y. Not doing anything with e yet. And this one, of course, should be all our favorite. There's simply nothing to plug in. So what do I have? I have quite a very, 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 very long expression, to say the least. I only care, however, about the x prime, y prime terms. Remember, that right there is why we cannot complete the square. Where did all of those come from? I just kept track of it. There's none here. There's some right here. Notice that these do have a factor of c, so I must include that. There are some here and some there. Notice those do have a factor of b, so I must include that. There's some here. Those have a factor of a, so I must include that. So I'm just going to ignore everything else except for the x prime, y prime terms. And hopefully I've not made a mistake and you guys have the same amount that I have. And what is our goal? Our goal is to have all of these be nothing, 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 nothing. I do not want any of them. I'm going to take the power of algebra, this value, and I'm going to figure out how to make it nothing, meaning set it equal to 0. I'm now trying to figure out what value of theta, notice there's a theta in every single one of these terms, is going to create this to be nothing, that to be nothing, 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 and nothing. Our goal is nothing. How am I going to do about this? I'm going to remember, I might have complained once to Mr. Kern about all the trigonometric identities that I'm forced to memorize. No, you memorize them because you understand them better and you recognize them better. Take a look at that. Take a look at those two together. Take a look at that, and you should be seeing what I'm also seeing, which are known as double angle identities. 2 sine of theta cosine of theta is the sine of 2 theta. This just have a common factor of b, so I just factored it out. Whoa, that looks vaguely familiar, doesn't it? And I have another 2 sine of theta cosine of theta is the sine of 2 theta. This you'll recognize is the double identity for cosine, so I'm going to throw that one in here. And notice I'm heading in a direction that is simplifying everything. Once again, my goal. I'm just trying to get this to be nothing. How am I going to do it, though? I've got to identify what the heck it is. So that and that are common. So maybe we can factor that out of those two terms. And let's maybe move this one over to the other side of the equation, which would lead me to here. I have c minus a sine of 2 thetas. I have negative b cosine of 2 thetas. Well, just for the heck of it, I'm going to divide both sides of the equation by the sine of 2 theta and divide both sides of the equation by negative b. That would lead me right to there. One thing I do not like, of course, is this negative sign. Most of you are naturally always going to take this -1 factor and apply it to the top. And this I recognize as the cotangent quotient identity from the units of identities. So using that, what do I have? I figured out that if I can find a particular value of theta that doubled, take its cotangent value, and apparently it's going to be equal to a minus c over b, it's going to lead me to my goal, which is to get this thing the heck out of there so I can complete the square. How do I solve for theta? That, ladies and gentlemen, was the purpose of the inverse trigonometric functions you developed earlier in the year. Let's do a quick review. This is what cotangent looks like. Cotangent, if you remember, is defined as x over y. We're never allowed to divide by 0, which is why that at 0 and at pi, which would have a y coordinate of 0, there's 2 vertical asymptotes. This is a function. It's a periodic function. It does pass the vertical line test, but it does not pass a horizontal line test, so it is not a 1-to-1 function. So you should have learned that we're only going to pay attention to one cycle, which is this cycle right here. So let's take this. Cotangent of some particular angle is going to be a minus c over b. Good to know. To solve for twice theta, I'm going to take the inverse cotangent, recognizing that I'm being restricted to talk about angles that are only going to be from 0 to pi, exclusive, of course, because of the 2 vertical asymptotes. Where does that take us? That takes us to here. If this particular number is going to be positive, and I know that inverse cotangents only address the angles from the first quadrant up to the second quadrant, then this must be in the first quadrant, which means twice theta must be some angle that is more than 0 degrees all the way up into 90 degrees, which means that single theta, if I divide both of these by 2, therefore is going to be constrained between 0 degrees and 45 degrees inclusive. If this number was negative, that means I must be working over here in quadrant 2, where cotangent is negative. So if the cotangent value is negative, then I'm talking about quadrant 2, but of course I cannot include 180 degrees because cotangent is not defined. And there's no need to include 90 degrees because I've already taken care of it with this first understanding right here. So solving for single theta means that divide both sides of this inequality by 2, nothing wrong with that, and I lead to there. So these angles of rotation are just going to be between 0, which means we'll never really not rotate, up to 90, but not a full quarter rotation. And that makes total sense because if I can show you guys really quick. Here's my Cartesian plane. Clean up a little for you. Let's group these. See, if this is my angle of rotation, there it goes. You see it? You know what I'll do? I'll clone this. There we go. Put all on top of each other. And here we go. Notice my rotation. Rotate, 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 rotate. And common sense says that, oh, I only need to rotate a quarter rotation because now I'm just back to something that maybe opens vertically. Keeping that logic going, humor me. It makes sense. Well, at this point in time, I already have things that open up horizontally on both directions, vertically in both directions. All I ever need is a rotation angle from 0 to 90 degrees, if you're ever wondering. So let's do this, people. I now have recognized this right here is going to go into my notes, and I'm going to highlight it. I'm going to identify what it is. This is the means of finding theta, the angle of rotation necessary to eliminate the x prime or the xy term and head to a language of x prime, y prime. Let's do one quick example with each other and show you how to derive it. Which conic is this? Typically, I would say, oh, it's two quadratic terms. They're the same sign. It must be an ellipse, but this is throwing me off. Let's use rotation of axes to eliminate this xy term. But to do that, we need to figure out what is going to be our angle of theta. Back to our formula. Cotangent of twice theta is just going to be a minus c over b. A is the coefficient of this term. C is the coefficient of that term. B is the coefficient of that term. I'm just going to put my numbers in. 1 minus 2 over root 3. Simplify the numerator. And ding, 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 ding. Now this really looks like something we did much earlier in the year, where we were able to identify particular angles based on 30, 60, 90s, 45, 45, 90s, and or quadrantal angles, meaning that the terminal side was on the positive or negative axis, either x or y. So the cotangent of twice theta is -1 over root 3. Let's figure out theta together. Since that value is negative, that's the first thing we want to make sure we understand, it means that our angle is going to be in quadrant 2. So I'm looking for what particular angle this is. I myself was always brought up think in terms of reference angles. I recognize this relates to 30, 60, 90, particular 60 degrees, which would be the reference angle, meaning that the actual angle itself was 120 degrees. And if the twice theta is 120 degrees, that implies that theta itself is 60 degrees. 60 degrees, one of those magic angles which I have memorized: sine, cosine, tangent, cosine, secant, and cotangent values for, just like this. Look, listen to my finger snap, you got them so quick. Just like that, ladies and gentlemen. You're knowing your ABCs in trigonometry at this point in time. Let's go to our rotation formulas. Now that we have identified the value of theta, let us plug them in. There they are. In both of these, in fact, all four of them, you're going to see constant patterns showing up as we work through this rotation problems anyways. Is a 1/2. I always like to clean that up myself. The less fractions I'm writing, in my mind, the less chance there is of making a notational error. Excellent job today. You now have the means of identifying theta. Look forward to seeing you guys in the future.